Potential energy, often denoted as U, represents energy stored within a system due to the position or configuration of objects. It's energy held in reserve, ready to be converted into kinetic energy or work. Crucially, potential energy is defined for conservative forces, where the work done depends only on the start and end points, not the path taken. Two fundamental types are gravitational and spring potential energy. Let's start with gravitational potential energy near Earth. When an object of mass m is raised near the Earth's surface, where the gravitational field strength g is approximately constant, it gains gravitational potential energy. The amount stored depends on its height h relative to a chosen reference level, where UG is defined as 0 by definition. The formula is UG equals mgh. Here, m is the object's mass in kilograms, g is the acceleration due to gravity, about 9.8 meters per second squared downwards, and h is the height above the reference level in meters. Raising the object increases UG, lowering it decreases UG. The work done by gravity as the object moves is equal to the negative change in UG, that is, W grav equals negative delta UG, highlighting energy conservation. For objects significantly far from Earth, such as satellites, or between any two masses m1 and m2, the constant g approximation fails. The general form derived from Newton's law of universal gravitation is UG equals negative g times m1 m2 over r. Here g is the gravitational constant, 674 times 10 to the minus 11 Newton meters squared per kilogram squared, and r is the distance between the centers of the two masses in meters. In this case, UG equals 0 is defined at infinite separation, as r goes to infinity. The energy is negative because gravity is attractive. Work must be done against gravity to separate the masses to infinity. Now, spring potential energy, also called elastic potential energy. When a spring or any elastic object obeying Hooke's law is compressed or stretched from its equilibrium or relaxed length, it stores spring potential energy. The force exerted by the spring is Fs equals negative kx, where x is the displacement from equilibrium. The energy stored is Us equals 1/2 kx squared. Here, k is the spring constant in newtons per meter, measuring stiffness, and x is the displacement from the equilibrium position in meters. This quadratic relationship means doubling the stretch or compression quadruples the stored energy. The work done by the spring force when it returns towards equilibrium equals the decrease in Us, that is, W spring equals negative delta Us. Like gravity, the spring force is conservative. This video about potential energy, gravitational spring, is part of our larger Physics 1 for Engineering students course. The course is entirely free and has more than 100 subtopics inside it. We're excited for you to try it, and the link is in the description.